Hello. Today I'd like to share with you a little bit about what I did for my final project concerning FEA modeling. In particular, I focused on modeling hardness indentation on two different types of material, looking at two different types of hardness indenters. Um, just to talk very briefly about what hardness indentation is, you have a machine that uh, pushes an anvil of a given geometry into a material specimen, and the type of geometry depends on which type of test you're running. So I chose to do a Bernal hardness, which is a sphere anvil, and a Vickers, which is an inverted pyramid of a very given, very specified um, angle between the two faces. So looking at the model, um, very standard, just made a cube for the material specimen, and for the indenter I also made uh, a box that I then cut off two triangular shapes to make a quarter of the pyramid, because this has a fourfold symmetry that can be exploited. The real crux of this model is defining the material properties, and so I want to kind of focus on that a little bit. If we look at this material, I plugged in a density and elastic values, which are pretty standard. But the real, when we come into looking at deformations, we have to consider plastic. And so Abacus has a couple different ways that it will model plastic deformation. I decided to try the Johnson and Cook. So online, I found some values for the two materials that I chose, which were a titanium 6 aluminum 4 vanadium, which is a very common alloy in many different applications. And then I also did an aluminum alloy, aluminum 6061, which again is very common, especially in aerospace. Anyway, this is the Johnson-Cook equation. So you have your yield stress, and then a derived equation, an experimentally derived equation, where the A, B, N, C, and M parameters are all fitted based off of experimental results. So I pulled those values from sources online, and these were the aluminum properties that I plugged in, and these are the titanium. So we can see in here, looking at the Johnson-Cook, they have the same values, and then you have to go to the sub-option rate dependent to plug in your C and epsilon naught, or epsilon 0. Once those parameters are plugged in, you could then put together assembly, very straightforward. Put the tip on the corner. The next is assigning steps. What I did was I assigned two static steps, one to indent and then one to remove. And so we'll talk about the interactions in a minute. The next part is the load. So I fixed the bottom so that it was unmoving, and then I made these two sides to be symmetric, so that the boundary conditions allowed a symmetry around these two planes. And then last of all, if we look at my other boundary conditions, this one I defined to fix this in all directions except for the direction where it will indent. And then these are the two boundary conditions where I displace this tip into the sample, and then I remove it on this step back to its initial position, associated with the two steps that we just looked at. The other trick with especially modeling two interacting parts are defining the interactions. So the main one here is just looking at these two surfaces. So you define your primary, which is typically your hardest one. This is a rigid body. That was the other definition that we gave to the Vickers. And then this is the secondary, which is typically the softer material. I did also create a property for interaction, which is just a frictional coefficient. So I defined a tangential behavior and then a penalty for friction coefficient of 0.5. All right. Last of all, we will look at the mesh. For this one, I chose to use tetragonal elements for the two parts because I thought they matched best the indenter shape, and so that the faces and the nodes would respond in a way that was very conducive to a pyramidal shaped indenter. I also biased the mesh towards the point of indentation so that I got the most concentrated information right around the largest stress points. So once after defining the mesh, we were able to run the job, which is currently running. I started at the start, so we'll wait till it's finished. Okay, I think I figured it out. So I just had some improper field variables or I didn't have enough of the field variables being selected when I ran my model the first time, so I had to rerun it. Anyway, now we can see the deformation of the model. So here it is. You can see that as the tip plunges into the sample, you get a stress field underneath it. As it progresses along, it gets larger and larger. So the real trick will be seen after the indentation occurs. Does it stay plastically deformed? And yes, it does. So for calculating the hardness, what I did was I probed on these values, the furthest indentation point, and it's somewhere in here along that diagonal. And then I took these deformation coordinates, calculated the diagonal length from the origin, which is 0, 0. And then I also, at step 15, calculated the magnitude of the reaction force. Okay, and if I probe on this point, I have a reaction force of absolute value of 12.2 newtons. When we plug that into the equations that we briefly showed earlier, I got a hardness value for aluminum to be 22 Vickers hardness, and for titanium 61. Unfortunately, these are vastly off from what we expect in the real world, and I attribute that to, for a three-dimensional model, our meshing isn't quite as, probably not as small as we need to actually measure the effect of the stress field and the resulting deformation. So I think meshing could be improved, and with a student license I'm limited to 1,000 elements or 1,000 nodes. However, I think the bigger problem is that the Johnson-Cook might not be the best in terms of dealing with non-spherical geometries. Because when I did the Brinell test, which we'll look very briefly at, it matched very closely with reality. So I think there's geometric factors that probably play into the Johnson-Cook a little bit more than I realized. And so I think either choosing a different deformation method for the plastic model, or having to do tailored Johnson-Cook parameters for specific geometries might improve the results. Anyway, let's take a quick look at the Brinell. So we'll take a look at the aluminum one. In this one, let's just jump straight to the assembly. So we have a spherical indenter on a very similar block of material. Since this is axial symmetric, I could model it in 2 dimensions, which really allowed me to improve the mesh. So as you can see, I was able to get a lot more nodes focused around this point rather than having to disperse it into a 3-dimensional body. Very similar loading conditions, interactions to what we did in Vickers, so I'll run this and we'll show those results real quick. Alright, and we're back. So the model ran, and here is the result of when we apply a sweep for the axial symmetry. We can model now more than just a 2D profile. So if I run this real quick, we can see the deformation being applied, and as it removes, we have a residual indent. Once again, here I picked this point, or one of these points, to measure the diameter, doubled that distance to get so I measured the radius, doubled it to get the diameter, and then similarly cut the reaction force here. And when I calculated these, I got a hardness for aluminum of 94 and a hardness of 312 for titanium on the Brinell scale. Compared to reality, these are very close. Typical aluminum is around 95, and so us getting a value of 94 is remarkably close. Likewise, for titanium, typical range is around 334, so our value of 312 isn't that far off. So I think this supports my the idea that the model does a lot better with rounded geometries as opposed to sharp corners. So there might be some tweaking within the models to improve upon indenters like Vickers. So thank you so much for your time and attention, and hopefully you were able to gain something from this demonstration.